going to tee up our first speaker. Dr. Bill Chappell is here from DARPA, and his message is going to be, and I'm going to be very simplistic about it, is what we should expect when it comes to the kinds of demand that are coming down the railroad track when it comes to mobile networks and wireless spectrum. And so if you use his viewpoint as really just a backdrop of what we can expect in terms of demand, then you understand why we're all talking about spectrum sharing and dynamic spectrum versus exclusive use. So please give a warm welcome to Dr. Bill Chappell, all the way from DC and DARPA.
All right, thank you, Tim. So I'm the director of the Microsystems Technology Office, one of the 7 offices in DARPA currently. And what we actually do is work that's need-driven, but actually really focus on the underlying technology, underpinnings of what we believe the next generation systems will be based on. So I'm going to walk through some of the work that we're doing that's in the laboratory that if you project 10 years may show us what's the art of the possible. So to do that, what I'm going to do is not just talk about my office, talk about what some of the other offices at DARPA are doing as application drivers, and then where that's taking the semiconductor work that we're doing, and then end with where we see that impacting this dynamic spectrum world. So there's 3 offices I'm going to focus on. BTO, which is the Biological Technology Office. It's actually our newest office at DARPA. And a lot of wounded warrior care as an example of what they're doing. They're also fighting infectious disease, and Ebola is the most recent example of some of the work that they've been working on. CTO, with large platforms, an example there is the work they did in the DARPA Robotics Challenge, which was held this past summer. And then I2O, with legacy from the initial internet demonstrations, but also now focused both on cyber and big data, but also works with certain spectrum aspects. So I'm going to walk through those 3 applications and then take a look at what's actually inside of our office as to what are the possible in about 10 years could be. So my office, if you think of what we've historically done, gallium arsenide was about $1 billion push to create the gallium arsenide industry within the United States. Now it's the heart of all military transmitters, and also still hanging on as the transmitter of choice for wireless systems. More recently focused on silicon germanium and gallium nitride and silicon carbide. So you're starting from basic laboratory demos where these materials are not ready for prime time, and then trying to create a national capability. We also do processing, so not just the materials, but the underlying processing work. This is an example of actually a fresh result where that base, the base material here, that gold color here is CMOS, so you have billions of transistors, but on top of that you're creating indium phosphide and gallium nitride. So system on a chip, which we think of as relatively low quality capabilities for wireless interfaces. You can actually start integrating in the good materials that we like for high power amplifiers and high dynamic range analog to digital converters as an example. All right, and we also do things up at the component level. This is just an example of the chip scale atomic clock. So this is a cesium competitive reference. This is about the size of a quarter. You can now buy this for about $1,500. Not relevant for mobile handset, but in terms of base stations having local time references that are equivalent to a GPS satellite is what this technology buys you. All right, so that's the type of work that we do. So we kind of look from the bottoms up and what the technology opportunity space is. So I'm going to walk you through some of the applications and where that's driving us. BTO, this is the Deca Arm. This is actually, I believe, the most advanced prosthetic arm ever created. You can see it's grabbing this grape and is not crushing that grape. And so the ability to have that level of dexterity is unique in terms of restoring capability for wounded warriors. But what's actually more interesting than just that prosthetic is how it's being controlled. So in 2011 we had what we call our first flight for direct brain control. So this is actually a quadriplegic who has a surface electrode array on top of his brain. And we call that first flight because this is one of, if not the first demos of a quadriplegic being able to restore functionality and controlling the prosthetic directly with the thoughts from that's being picked up by that surface electrode. So that's 2011, and what's exciting is from 2011 to 2012,
and open it.
right, we got substantially better.
Back.
That is just the most astounding thing I've ever seen. Can we shake hands?
Sure.
No, really.
Yeah.
Like, come right over here?
Yes, you come over
Okay.
there. Grasp your hand there. There we go.
Oh my goodness.
Yeah, so in 1 year, we were able to go from a very crude demonstration to actually showing the power of the brain. And actually, if you look at what's going on here, we're actually in much deeper stimulus, or actually recordings from the brain, because we have this deep the Utah electrode array. We went from a surface into a much more intimate contact with the brain and the neurons that we're trying to record. What was really happening is the brain is a lot more fascinating than I think we've always thought it was fascinating, but it's a lot more resilient than we expected. If you give the brain the ability to learn, what you'll see is its ability to adapt. Even if you're not sending the exact right signals, the adaptation in the brain is quite dramatic. So our ability to interact with the brain has just begun. It's a big push at DARPA. The limits will be the ability to put electronics actually within the human body. And so that's an interesting limitation. It's a question for the electronics community. What is it that we're going to be able to do to dramatically lower the amount of computation you can actually afford to put local? You're not going to be sending terabytes of data from where these neurons are being picked up. That's just not going to happen. You're going to have to call that data locally. So we're going from the electronic side, from low power, and a lot of people are doing low power electronics, huge focus obviously, running the race to Moore's Law. We're actually trying to make that next leap to no power. And a no power circuit is an example of this appendage that goes to low power electronics that wakes up based on an event. So in the wireless space, what you can imagine is something that doesn't have a wake up cycle, something that actually can be fielded for years because it's truly off, but still aware of its surrounding environments. This is really hard. This is the type of thing DARPA takes on, where we realize that the Internet of Things and everybody's trying to push millions and trillions of sensors to be deployed. That's not going to work if you're actually having to change the battery routinely. Right? So if we're actually going to have ubiquitous sensors, we need a way to conserve that battery life with a underlying revolution. So the information contained in the signal that you're looking for is actually what is going to wake up this signal. Right? So right now, I call our systems what we call first parenting, for first child parenting, meaning you wake up every 20 minutes and make sure everybody's alive and still everything's going well. Right? So now you have third child parenting, right? Which is you're sleeping, you hear a cry from the other room, you try to detect, is that worth waking up for, right? Or not. So that's the type of shift we're trying to make, is you're actually starting to be alert of your surroundings even though you're truly off. And so let me walk you through what that looks like. And our signal comes in, it's got a chirp, it's got some sort of temporal features. This might be a microvolt signal. We're looking around minus 80 to minus 85 dBm. That goes through a passive processing and transformation. Right? We believe, but there's other ways to do this, that this may be advanced acoustic signal processing that's required to be able to take that signal from its microvolt stage and bump it up an order of magnitude, or 2 or 3 orders of magnitude. We would then pass that through passive gain. So now you're doing passive match filtering. Again, potentially the acoustic domain, where you're collapsing the features of the signal that you're looking for into these impulses that are now going to be maybe millivolt levels, and if you're millivolt levels, you can create transistors that will snap on and wake up the rest of that system. So this program, the mandate is less than 10 nanowatts, so the continuous draw of this system that is off has to be lower than a typical battery has in regards to just natural leakage. Right? So this system would basically last as long as the battery that's supporting the rest of that system, and the fact that it has this wake-up feature wouldn't be the defining feature in how long that's going to last. So this will work inside the body. If you're looking for specific neural signals, it will work inside of RF networks, as you can actually start synchronizing very differently, right? And you can actually wake something up to an event. Every packet that you want to wake up the system, you'll send a specific key that will make that system turn on. All right, so that's the bio work. TTO is our structures office. You might know it from its stealth work that it invented previously, but it's had a lot of focus on autonomy. And the big focus there was the DARPA Robotics Challenge.
Loading the dress room.
So you can see it definitely was exciting. We held this at a racetrack in California, and actually had thousands of visitors to be able to watch this competition, and a surprising amount of empathy for the robots actually as you watch them try to go through this course. And it definitely points to a different future in our relationship with the machines around us. Having said that, right? So we got a long ways to go as well. This DARPA's role is to take a look at what is the state of technology, not be afraid to publicly fail. And we have the leash and the goodwill of the public and sort of our administrative change to be able to look very squarely at what the state of technology actually is. So what this does, it points to a very different future where we have interactions with machines that's very different than we have today, but it also shows the importance of sensors and smarter processing that are still required. A lot of the failures that we're seeing is actually when we really focused on autonomy, where we cut off the network connectivity. Right? So how it relates to the spectrum work that you'll be talking about today is, we're working with a support system, either intelligence in the cloud, but also human support, working through that network. Through that challenge is actually the series of challenges that we've focused on were things which, if we could do them with robots, would have helped with the machine manipulated today. So we challenged them: can you turn a valve? Can you drive a golf cart? Can you walk up a ladder? And in various parts of that course, we actually turned off the network connectivity, and that's really where it became very hard. It shows the amount of work that we have, both in creating robust connectivity, but also then autonomous capabilities inside of disparate systems. All right, so LiDAR is the heart of a lot of what that capability is utilizing. So really, most of the UAVs that are doing mapping are self-driving cars, and again, this is the Atlas robot that now is purchased by Google, but initially was developed by DARPA. That's a LiDAR that provides this situational awareness around it. These are still expensive, and a huge limitation in terms of having the perception that you and I would have as we easily walk through that course that we set up. So those are a problem. What we've done recently is taken the electronics Moore's law scaling, right, which we are probably all aware of, right, in terms of this revolution that's provided the digital capabilities that are the heart of our systems, and started to look at a different path, right, which is integrated photonics. So this is the first ever demonstration of writing MIT, right, with a laser beam, which is distributed through a fiber, distributed through 10,000 optical components. This is now getting into mass manufacturing of optical components, much like we expect in our electronic systems. It gives you the tolerance, it gives you the integration density that allows you to rethink what is an optics system and where photonics is going to lead us. This is a baby step. We're now developing a full LiDAR on a chip, leveraging these types of technologies. So you can imagine a robot walking through this complex world, right? We're asking it to turn its head, right, and try to keep track of what's around it as it's doing that rotation. This MIT is written on the wall with a fixed sensor, which would be an equivalent of peripheral vision, or at least focus within the vision of that system. So it's not just about that better sensor, it's that processing behind it that we think is actually going to allow for a lot more intelligence to be built into the system. What we're getting good at are things like deep learning for image tracking, so pulling out information from complex environments, and so we do that sort of routinely today, and you'll see that in a lot of our systems. Even when you go on the internet today, there's a lot of machine learning behind those systems. Our focus is actually looking at things like analog probabilistic processing instead of doing that digitally. How would we put that level of intelligence forward into our system? So instead of tracking 1,000 targets in a complex scene, let's say something around 30 watts, if you do that in analog, we're looking at 100,000 targets at around 5 watts. So you're now starting to impart that knowledge that we're expecting that's coming from the cloud that's supporting our systems and putting that locally into the system. And we're getting pretty good at that. What we're not good at is action and context recognition. So we're really harvesting the second wave of machine learning as it exists today. This is actually, impacting us in a variety of different ways. You can't read scientific news articles today without hearing about the beauty of machine learning. It's really powerful, but it's really quite bad at actually real-time recognition of unexpected events, having action and context recognition. So we have a program underway which we call Cortical Processor, which doesn't just recognize that this is a girl, but that's a tennis racket. It actually puts the verbs in between. So we can actually do action recognition, so we know not just the instantaneous event that's happening, but the actual relationship of all of the images that are in the scene, and specifically when they're moving. To do that, an example of what IBM's doing is building saccadic vision. This is how we look at a face on the upper left there. We don't actually look at a face by looking at every pixel. We're actually much smarter than that. Our eyes are continuously moving, continuously scanning. We scan in a very specific pattern. We recognize the separation of the eyes, the cheekbone structure, certain aspects of this. And this is the type of movement that we know that the human is doing. We don't do that typically in our image processing units. We don't do that in the RF space, as an example, when we actually intelligently look for signals. We usually try to capture everything and try to absorb all of that information all at once. So an example of what saccadic vision will do is I'm looking at a small portion of this chaotic scene. I think that may be a giraffe. Let me go look for the neck. If a giraffe's going to have a long neck, let me then start adding this probability of likelihood, right? Even though I went from 10%, it gave me enough of a cue to tell me where I need to start processing all of those pixels. And this is the type of algorithms that we're looking at, which we call hierarchical temporal memory algorithms, that allow you to have this intelligence. All right, so this is kind of a long lead-in to where we think the spectrum is heading. Right? What I showed you are ultra-low power electronics that we're going to put in the field, even in the body, but also just distributed across the field, and sensors and smarter processing that we believe will be the revolution, not just from the second wave of machine learning, but this third wave of machine learning, where we actually have context built into the analysis that we're looking at. And I2O started a program which we call the Spectrum Challenge, and the Spectrum Challenge starts to challenge the community. How do you take this level of intelligence and actually start using it in the spectrum? So this is what it looked like. This was, I would call a nerd fest, right? So this is about 90 universities all converging on DARPA, being given 5 megahertz worth of spectrum, no policy, no plans, figure it out on the fly. Right? So what is it we can do if you put the decision inside of the machine, right, instead of the policymaker itself? It turns out, right, as I think people here may have guessed, right, spectrum sharing is the right way to do it, dynamic spectrum sharing. You could always have said, you stay out of my way, I'll be over here. Right? That turned out to be a very efficient way to approach it. Figuring out where the opportunity space where it resided, even though it was 5 megahertz and relatively small, actually filling that, being opportunistic and where that opportunity was, it was a huge leap ahead. But this was relatively small. This was 90 universities. It was 3 radios challenging against each other. So 3 radios, not large scale, 5 megahertz, not large bandwidth. But it does show some intriguing capabilities for the future. So if I go back and say, what was my flip phone a decade ago, right? This was the frequency allocation. So our challenge that we just ran was like one channel within one of these bands. So you go over time. This is the type of radio that you may purchase today, or at least under development. These are some of the more recent standards which are being fought over by people like with the likes in this room. DARPA has a new chip that we go from 20 megahertz to 20 gigahertz. We call this the Art of Fpga. So it gets past this idea that we have fixed bands, right, that are standards driven, that give you the isolation between one radio network and the other. This is actually a dynamically programmable system, much like we have for FPGAs. Right? You're now designing and having a very intense design cycle for an FPGA that is scrubbed from the actual specifications how it's used. We don't have that in RF. In RF, we actually create standards that we go off and try to meet the requirements of those standards. That means we're always going to be developing, right, in the rearview mirror, right, for what we analyze, what we think is going to be needed years prior. Right? So what we're doing with the RF FPGA, especially from a military perspective, we don't always have a standard to design to. Right? We need to build that flexibility, so when we're in the field and something may have not been planned correctly, we have the ability to adjust. So what these boxes are here, this is actually local oscillators, so there's many, many different local oscillators across that chip. These are the baseband units, and inside those baseband units, each of the amplifiers is tunable, the mixers are tunable, and we actually have multiple mixers within each of those blocks. These are the millimeter wave blocks that go along with it. So right now, 20 gig and below, we're thinking of going up to 40 or higher. And so this chip has 2 to 250th states built inside of it.